Imagine trying to measure a mechanical component, only to find that the edge falls halfway between the 1 and 2 millimeter marks on a ruler. In engineering and physics, guessing 1.5 is a risk. We need physical tools designed to remove human estimation from the measurement process. This is the Vernier caliper. It features two primary measuring interfaces: large external jaws for measuring widths, and smaller internal jaws for checking internal gaps. The caliper's architecture relies on two overlapping tracks, a fixed main scale and a sliding vernier scale. Achieving sub-millimeter precision requires abandoning the single point of reference and using this dual-scale comparative system. Every instrument has a least count, the absolute smallest physical distance it is capable of recording. The vernier scale is designed so that its divisions are slightly smaller than those on the main scale. By compressing these divisions into a shorter total length, the tool creates a microscopic mismatch between the top and bottom tick marks. We define this physical limitation mathematically. By subtracting the length of one vernier scale division from one main scale division, we find the exact value of the least count. For most standard calipers, this algebraic derivation results in a precision limit of 0.1 millimeters, or 0.01 centimeters. The physical design of the tool uses this algebraic relationship to convert a tiny spatial difference into a readable measurement. To see this applied in practice, we will use the instrument to precisely find the diameter of a metal wire. The first step is to locate the zero mark on the sliding vernier scale. In this example, the zero rests just past the 11 millimeter line on the fixed scale. Sometimes the zero falls into an ambiguous gap. Here, it lies somewhere between 10.2 and 10.3 centimeters. We record the main scale reading as the lower value immediately preceding that zero line, in this case, 10.2 centimeters. This provides a baseline measurement before we calculate the additional sub-millimeter fraction. To find that fraction, we scan the sliding scale to find the single mark that perfectly aligns with any mark on the main scale. In our example, the third vernier division aligns, giving us an n value of 3. We synthesize these values using a standard formula. The total reading equals the main scale reading plus the product of n and the least count. For the wire, we take the 10.2 centimeter baseline and add 3 times the 0.01 centimeter least count. The final result is 10.23 centimeters. This process converts a visual alignment into a specific recordable measurement. However, physical tools are subject to wear and mechanical damage. Over time, a caliper may lose its alignment. You check the tool's integrity by closing the jaws completely. With nothing between them, the zero marks on both scales must perfectly align. If the lines are disjointed, the instrument has a zero arrow. If the vernier zero is to the right of the main zero, the error is positive. The tool is registering a measurement before it has even been applied to an object. Identifying this mechanical misalignment is the necessary first step toward ensuring the accuracy of a final measurement. A negative zero error occurs if the vernier zero slips to the left of the main scale zero. This requires a specific formula to determine the offset. Consider a problem where a scale has 10 divisions and the fourth aligns while the zero shifts left. We subtract the coinciding line from the total divisions and multiply by the least count. Here, the tool undercounts by 0.06 centimeters. To fix any measurement, we use a universal correction. The correct reading equals the observed reading minus the zero error. Subtracting the negative error from our 1 centimeter measurement reveals the actual length, 1.06 centimeters. Scientific accuracy depends on the mathematical literacy to recognize these instrument flaws and apply the necessary corrections to an imperfect tool.